when we have a worm and a worm gear, or when we have two objects that are rotating against one another, okay, that are not two gears. So in this case, this guy's not actually, well, he is rotating, he's turning. The top screw part is actually just rotating. But the fact that all of those indentations are made on an angle, all right, means that as they actually turn, they're meshing and they're causing the actual wheel to turn underneath them. But just like in a direct transmission, remember, they're touching. They are directly in contact with one another. Okay, the contact is happening right here. And if we have direct contact, we know that the driver is always going to go whichever direction, and the driven, okay, or the second object in that train will always go in the opposite direction. And we see that here. Whatever rate, okay, we'll talk a little bit about speed here, whatever rate the driver is going at, the driven will go at the same rate. So if in 1 minute, the top part here, the driver makes 10 circles or 10 revolutions or rotations, then the gear train here will actually move. So if we start here, it will actually move 10 teeth. 1 tooth for every rotation. Okay? Is there a lot of friction in this system? Where is friction happening? Friction is happening everywhere that these guys come into contact. Okay? This can also elicit a lot of torque, a lot of power. We'll often see these kinds of things in heavy machinery that has to drag big loads or move large amounts or withstand really, really high amounts of pressure or heavy loads on top of them. Okay? Heavy machinery. It's a lot of friction, but it produces a lot of power and it actually transmits the motion really well. Okay? So changing gears, we're going to talk about speed changes. All right, and we're going to use this image because we've already got it up here. Speed changes in a worm and worm gear system are kind of pretty easy. If you change the speed at which one of the components is turning, it's going to affect the other component. If this driver, the worm, the driver starts turning faster, it's going to cause the actual gear here to turn faster. Okay? The same can be said about pretty much any type of transmission system. But when we talk about other types of transmission systems, mainly a gear train, if we look at this guy here, okay, we've seen this image before. If we look at this guy over here, what do we notice about gears A, B, and C?
They're all different sizes.
They are different sizes. So if there is a motor that is turning one of these gears, okay, if you have a gear train and you have direct transmission, right, they have to touch one another. Well, one gear is not going to be able to go really, really fast, and then the other gear is going to go really, really slow, and then the third gear is going to go medium, unless they're different sizes. Because whatever the rate of that first gear, gear A here has a specific size. And if we go back to that GIF and look at the actual image, we'll see that it takes a set amount of time for it to make one complete revolution. A complete revolution of that involves leaving from starting point, getting all the way around back to starting point. That is one revolution. And that is going to be dependent on the size of the wheel. The bigger the wheel, the longer it takes for it to revolve. Okay? Now, which one is bigger here? Wheel A or wheel B?
B.
Wheel B is larger. Wheel B is larger. So is it safe to assume that if on wheel A, you've got, I don't know, like, let's say 20 teeth. I don't even know how many. Oh, actually 30 teeth. There you go. But I don't believe that. No, you don't have 30 teeth there. You might have like 20 or so. Anyway, whatever. It's not important.
17.
There you go. It's safe to say that in any gear train, the width of the actual teeth, in order for the gears to mesh, the width of the teeth have to be the same, right? You cannot have the gear next to it with bigger teeth or smaller teeth because they won't fit, they won't mesh. So how we can change speeds has everything to do with the amount of teeth. Okay, if we look at this, let's say this guy has 20 teeth. 20. And this guy has 30 teeth. And this guy has 10 teeth. Let's just say. Probably not right, but let's say. If they're rotating at the same rate, okay, if it takes them both, if it takes the first one 5 seconds to make a complete turn, that means that 20 teeth will have gone through in that 5 seconds. As it's turning, it'll go. And by the time we finish, time we shut it off, all 20 teeth have passed the starting point. That's one revolution. If 20 teeth of the first one pass one revolution in 5 seconds, will the 30 teeth of the second one pass in 5 seconds? No, there's still going to be 10 teeth that have to make a complete revolution, right? The more teeth you have, the slower you are. Okay, when we're talking about speed changes. So when we're talking about speed changes with gears, the bigger the gear, the longer it takes for it to make a revolution. The same is true for the opposite. If you've got a gear, if you've got a driver gear here, gear A, that's got 20 teeth, and you've got a driven gear, the third gear in the train here, that's got 10 teeth, in the amount of time it takes driver A to make one turn at 20 teeth, how many turns will driver C make, or driven C, I should say?
2.
It'll make 2 full turns. So which one in a set amount of time will have more circles? C will make more revolutions because it's smaller. So if you want to increase your speed, okay, your last gear needs to be big or small? Small. If you want to decrease your speed, okay, exactly. The last gear needs to be big.